page with respect to notation. And then later on we can venture out to more interesting stuff. So here's some introduction. We would like to infer some parameters. Typically this is not feasible to directly measure them. What you see here is not legal in most countries at least. So we need to find a way to probe the domain in some other fashion, and we can come up with some experimental design which really describe how we're going to collect the data. And this is impedance tomography that have been described over and over in the last 2 days. And once we collect the data, we can come up with an observation model that really embodies the physical relations between the model and the data. And obviously it's not free of, the measurement itself is not free of any noise, so we have noise and we have model inadequacy, so we encompass everything in this epsilon, but this is a topic of research by itself. And as we all know, if we try to naively invert, just try to minimize the misfit between, or some discrepancy between some sort of discrepancy between what we predict the data to be and the true data, typically we fail. So here is an example. That's the E. coli bacteria. That's the true model. Let's say that we were asked the student to take the measurement, and the lens was not in focus, and there was some noise on, or dust on the lens. The pseudo inverse will provide us this result. It will probably be the same for his grade for the class, right? So what we typically do, we try to incorporate some a priori information in the recovery. But if we look at this formulation from a really holistic perspective, taking one step backwards, there are actually many questions we can ask. So starting with the first question, as an optimizer, you can ask yourself, how can I solve this problem faster, bigger, larger, and so forth, right? So this is and there are many things that you can do, right? Just on that regard. Second question is, how can you model the physics in a more appropriate way? Higher order approximations, better geometrical representation, and so forth and so forth. And if you do that, you can get rid of some of the model let's call it inadequacies that you may have from some reasons, right? Next thing that you can do is obviously you can ask yourself, and that will be the topic, or one of the topics of today's talk, is how can I extract more information already from the measurement rather than relying on the somewhat bogus term that we have on the regularization. And another question, and I think Erki was touching that in some regard, is really how can you model the noise in a better way, right? Because the assumptions that we typically take about Gaussian noise are very convenient, but not necessarily true in reality. Next question is, of course, how can we incorporate more meaningful a priori information, and this is what that will be another topic that we'll discuss today. Some of Simon's talk was related to incorporating multiple modalities together, which is a challenge by itself. So that's another question we can ask. Of course, we can ask ourselves, we are not maybe interested only in getting a single point estimate, but we're interested in getting some understanding of the posterior. How can we sample the posterior in a better way? And lastly, the last question is really, in many situations, we are not really interested in getting the model itself. The model is, let's say, an image, but I really would like to know whether a patient has a tumor or doesn't have a tumor. That's really the end goal for me, and rather than getting a nice image, or whether we hit that nerve or not, right? So today we'll focus on these two topics, experimental design and learning regularization, effectively. So just to wrap up the three different challenges that we can identify. So the first thing that we learned in the evolution of inversion was actually how to simulate, how to describe the problem. So given a model and some observation or physics that we can describe, try to estimate data. The second problem is really the inversion. Given the data and some observation, try to infer the model with some uncertainties. And the challenge that we are advocating to try to look into is really the art of prescription design, given some inversion scheme and some knowledge about the observation model, try to find the best experimental design, the best regularization, the best control, the best decision, and so forth. And some of the philosophy that we try to put behind it is that we only stand a chance in trying to tackle those large-scale, seemingly intractable, complex problems of description, prediction, and decision under uncertainty if we come up with some approaches that are both teleological, and this is the meaning of that word I didn't know myself, so it's actually the philosophical doctrine that we're really looking at the end goal, at the final cause of what we are trying to do, and we try to exploit structure as we do that. So or in simpler words, it's better to have an approximate answer to the right question rather than an exact answer to the wrong question, as we often, at least on the industrial level, we often pursue. So let's start with experimental design. Some of you may know me from my previous life. I actually worked in a neurophysiology lab, and one day they came to me with data of EIT and asked me do the reconstruction. That was my role. And I did a reconstruction. I got these 3 nice images, and based on that, this is really the foci of epileptic seizure. So later on a surgical procedure, somebody would scoop out that part of the brain. And I was quite content. I got actually nice reconstructions until I heard that it is actually the same patient, simply different way of collecting the data, which can be scary if you are the patient or if you are the surgeon that does not have a good insurance. So other examples for data collection, so we spoke about the optical tomography. One of the questions we can ask is where should we put the sources and receivers? In what sequence should we use them? What intensities we would like to use? Other experimental design questions in electromagnetic inversion on the geoscientific level, you may have a coil that through which some electrical current is passing, and then you would have a magnetic field which is induced. Another coil will read the response of the subsurface, and that aperture will be traveled around the domain. And you can ask yourself, what frequency should you collect? What trajectory that donkey or truck or whatever should take? One of the hottest topic in seismic inversion is called combined sources or simultaneous sources. So in seismic inversion, you typically have this boat, and it sends some pressure waves into the ocean floor. These interact with matter essentially, and then we have another boat that carry those hydrophones, and we record the response of the subsurface. And one of the questions is how can you combine sources or combine receivers in a better way to so that you can either shorten the acquisition time or shorten the computation time of the inversion. Last question, I think the last thing that we can ask ourselves, or not last, but another question that Sirtanian was asking is, in limited angle tomography, how many projections do we really need? How accurate these should be collected, to what level of accuracy, and so forth. So there are many questions that we can ask with respect to experimental design. But if we summarize them all into several categories, one category would be obviously what is a design layout, right? And as you can see, we weren't the first to publish on this topic. So do you know where it is? It's actually nearby, I suppose, right? Stonehenge. Couple of hours. Okay, I won't see it on this visit. Then another question or another topic related to design is what should be the experimental process. And again, some people were tackling that problem before us, but especially in chemical experiments, that's very important. Now, you can be very creative about the design of the data collection paradigm, but you have to bear in mind that at the end of the day, you either have to face some constraints. So if there is a minefield, you cannot position your sources and receivers in the middle of the minefield. There might be some other safety regulations, such as the amount of radiation you can imply upon some organs in the body. Or you may have other preferences, such as time, cost of collection the data, and so forth, right? So you would like to incorporate all those constraints and preferences in your design. So now, if we be back to that equation, if we look at this equation, what we will try to do is to find a way to prescribe those wise parameters, the experimental design, in a better way. Now, previous work, for well-posed problem, we saw hundreds or even thousands of papers that tackle the optimal design problem. For ill-posed problems, we only found 2 before we started our own research. And we found it a little bit awkward and odd because, as we all know, many problems in engineering and sciences are actually ill-posed underneath the hood. And the question is obviously what makes nonlinear ill-posed problems so difficult or special, why people have not tackled them. So to explain that, I will first explain what people have been doing for well-posed problems. So for well-posed problem, you can take a Tikhonov regularized least square solution as your estimator, which is what we have here on the top. So assuming that, let's take the assumption that we have a linear model. So it's just a product of an operator that is independent of the model by the model. This is the estimator we have. And if we look at the difference between the estimator and the true model on the expected value level, we can decompose it into 2 components. One will be the variance, which is independent of the model, and the other will be the bias that is actually dependent on the true model. So now, to remind you, we are talking first about a well-posed problem. So for well-posed problem, I actually don't need regularization. So this whole alpha term, I actually put this alpha with G is irrelevant. So I can actually null it and end up with. And since the trace operator is a cyclic operator, I can take this A transport to the other side, and that C is nothing but the Fisher information matrix. All I need to do is to minimize the trace of that inverse information matrix. And this is called A optimal design. Now, you can think about it in a more holistic way as A optimal. It's called A optimal because it's average. The trace has a meaning of an algebraic average of the singular values. If you take the same matrix and you take the determinant instead of the trace, you can actually think about trying to minimize the volume of uncertainty, because the determinant has a meaning of volume. Or you can be very pessimistic and think about trying to bound the largest eigenvalue of your error, and that will be the min-max approach. It's called e-optimality, but then there's a complete alphabet of criteria that one can come up with in order to prescribe an experiment. Now, it all sounds very, very nice and convincing, but it doesn't really work for the class of problems that we are dealing with. So because the problems that we are interested in are nonlinear, you cannot have this closed form bias variance decomposition, which was neat because we could actually do some things. And even if you could have done that, because of the ill-posedness, controlling only the variance would not really bias that much, because most of the error is actually in the bias term. So what strategy can we use? And this is what most people are doing, at least in the industrial level. It's called trial and error. So we pick up a model, and this is the Marmousi model. You may have. We can come up with some propositions for experimental design. So on the left, we may decide to put some sources only on the side. On the right, we would put some of them on the side and some of them on the top. And then we can simulate or collect data. And obviously, we can then invert for that data. And really now it's up to us to decide which one of them we like more. And let's say that I prefer this one, so I would choose the experimental design that provided that recovery. Now, it all sounds very convincing, right? But bear in mind that that strategy only holds for the specific model that I provided, right? And only for a small selection of designs that I introduced. So what else can we do in a slightly more professional way? We can try to minimize both the bias and the variance altogether, but then we need to define some optimality criteria to do that. So now looking into the statistical merit of how to do that. So one option would be the loss function. The loss function would be really trying to measure the discrepancy between the models that we recover for the designed experimental design parameters versus the true model. Taking that discrepancy makes sense, but it depends on the noise that we don't know, and it depends on knowing the true model that we don't know. Then, of course, we can take the expectation with respect to the noise and look at the mean square error. But again, we are stuck with the fact that that requires us to know the true model, and in most situations, we don't know the true model. If we know the true model, we will not collect data in the first place. So we can repeat that trick, right? So we can take also the expectation with respect to the model space, which sounds reasonable. That's called the Bayesian risk. But computationally, for problems that are more than 5 or 10 variables, this is really not a viable way forward. So what can we do is what people have been doing in machine learning for a while. We can come up with some authentic examples of models, so some samples of the prior if you want. And we would try to find the experimental design parameters that the recoveries for those models will be as close to those authentic examples that we provided. And this is called an empirical estimate of the Bayesian risk, just to put things in the context. Now, it's not completely perfect, because you remember we had that big mushroom at some point, meaning that we would like to do more than that. This would provide us some designs that are either not feasible in practical settings or not optimal with respect to what we really care about. Maybe we would like the collection to be very, very fast. We didn't say anything about that to the design, so obviously we won't get a fast or low-cost design. So obviously we need to incorporate another term, either as a regularization or constraint that will penalize for designs that are not compatible with our preferences. So one of the questions is really how many samples do you need? And that really is a question of what type of character one is, not whether you're good, bad, or ugly. We spoke about good and bad Helmholtz, but we're not talking only about that. But really, like, you can be an optimist and would say, okay, if something works for that model that I work with, it would obviously work for everything else. And we know some people that do that. You can be a complete pessimist and believe that Mother Earth will screw you up irregardless of what you will try to do. So no matter how many examples you would provide, reality would be completely orthogonal to anything that you've introduced. And obviously we can be also a realist, right? So we can find some sort of compromise between the two. And I typically say that there's another type which is of person which is me, but okay. So now let's look a little bit closer into what do we do with respect to the design. So I mentioned that we would like to incorporate some preferences with respect to the design. So one preference would be to have a small number of sources and receivers. So if we look at this experimental design, let's assume that the green ones are sources and the red ones are receivers. So here is one example experimental design setting. So 1, 2, 3 observations versus 1, 2, 3 observations. Obviously, the observations here are far sparser than the one we had before. Okay? We have a far smaller number of sources and receivers on this experiment versus the other one. So in order to incorporate that, what we do is if we look into the PDE, many problems we can write in the following form, right? So the observation model will be some sampling operator. This is the differential operator that its inverse is applied upon our sources. So for many problems, if we take the sampling and the sources and let's say we call them both y, and we put some p-norm penalty upon both of them, that will induce them or cause them to be sparse themselves. So we would like the sources and receivers to be of a small number. And the problem with that approach is it's actually a good approach, but the problem is that you do need to explicitly have the link between the observation and your design parameters. And in some problems, it's quite difficult to derive that. You need to have a good handle for those relations. It is effective when you would like to have a small number of active sources and receivers. An example is, you may want to send somebody to the North Pole to collect data, and sometimes it's not that easy to do that. You need to fight with the polar bear over the space, and sometimes over the equipment, and in some situations even getting back to the camp is not easy, right? So now here's another example for an experimental design. So let's say that I would like to have a small number of projections, as Smolly was mentioning, right? How can I do that? So here is one example. So taking one projection, another projection, 2, 3, 5, 100, 1,000, and that would take a while and may impose a lot of energy that is being delivered to the poor patient, as opposed to 1, 2, 3, and done, right? Obviously, we would prefer this experimental design upon that one in some situations. So how do we do that? We essentially discretize the design space. So we rewrite our observation operator as dependent on each one of those potential candidates for experimental design. And then for all those candidates, we actually add a diagonal matrix that whenever we have an entry on the diagonal which is significantly larger than 0, essentially it means that we have a reasonable standard deviation, and we will collect that experiment. If it is close to 0, we will just throw out that observation. Now, in order to induce a small number of which, we can actually add a p penalty to this w on the diagonal. So most of those w's will be 0. Few of them would be non-zero. And solving this problem, essentially, this design problem, would provide us an experiment that has a small number of observations. Now, we have to bear in mind that so far I spoke about the design problem. So the design problem is really an upper level optimization problem in which the lower level of optimization is really the conventional inverse problem that we are trying to solve normally. So if we found this challenging by itself, we actually need to have another level of optimization on top of that, which is quite tricky. So this is a bi-level or multi-level optimization problem, which can be unpleasant to resolve. And these are the two different formulations for the one with for the two types of penalty that I mentioned. Just an instance of how to address that. So for the second one, when we had those weights on the diagonal, with some assumption, let's say that that the lower level of optimization is convex with well-defined minimum, and we don't have inequalities, we can then substitute that lower level of optimization with the first order necessary conditions for stationarity, and then we can essentially replace it with this equality constraint, and from there the solution is far easier. So we can eliminate the dependency upon the model through implicit differentiation. So we differentiate the constraint with respect to the models. We differentiate the constraint with respect to the experimental design parameters, and then we can get the sensitivity essentially through a chain rule of the two. So once we have that sensitivity, we can write the reduced gradient, and we can essentially, once we have the gradient, we can solve the problem. So let me show you some numerical studies. So the first one is with impedance tomography. We have the div sigma grad with some boundary conditions. We use the finite element discretization in this case. And in that specific setting, we wanted to reduce the number of sources and receivers that are active. So here is a recovery of the true model, or not the recovery, that's the true model itself. Here is a recovery with naive design. So you can see this huge artifact at the other side of the head, meaning that this guy would actually have to pay twice to the medical insurance for 2 surgeries, and this is the recovery you can get when you optimize the experimental design. So we can see that making this sort of exercise can be detrimental in some situations. Let me show you another example. So magnetotellurics imaging, we use passive sources, so solar winds and remote thunderstorms are our sources. Typically, because they're so remote, they can come as planar waves, so they have excellent penetration depth. The low frequency components actually have better depth, but lousy spatial resolution. The opposite holds for the high frequency components. Here we use the full Maxwell equation, discretized on a finite volume setting. And what we wanted to design in this experiment is what frequencies we would like to collect the data. Since we cannot control the sources are whatever is given, we can only control what frequencies we would like to listen to. And that was the second formulation that I showed you. So here is an example. That's the true model. Here is what you can get with a naive design in terms of recovery. And this is the recovery with an optimal design. And you can see better definition of the shape and the intensities. But more than that, the variability is actually smaller, and that's even more important. So you manage to mitigate uncertainty, and that's even a bigger win of that approach. Now, as Bill mentioned, I now work for IBM Research, and we work a lot with the industries. And for them, a fundamental question is whether to drill or not to drill. An offshore platform drilling can cost $250 million. 2 out of 3 are actually dry, so $500 million can be just thrown to waste because of not following a good exercise of experimental design where you should really drill. So you can repeat the exercise of doing experimental design with different budget of resources, different budget of whatever resource you decided to provide. Either it is projections or whatever, or sensors that you would like to deploy. And the interesting thing is then you can actually see how your risk is being reduced as you add more budget, right? And this Pareto curve is actually very important for the decision makers, because they need to decide whether it's really worth for them to go for one type of survey or another, and the implication with respect to the risk that they would take and the trade-off is actually very important. Here is a very recent study that we did. So I mentioned that in seismic imaging nowadays, people are trying to combine sources together. And so the governing equations are the Helmholtz equations here, the acoustic ones. And the observation operator, so in this case, essentially, we combine the data as well, because the linearity of the forward model with respect to the source, we would like to combine the data together. And the question is, how do you combine sources in a clever way so that you can get better recoveries? With either you can do it on the fly, so while you not on the fly, but while you're collecting the data, so you can collect far smaller number of you shoot far smaller number of explosions, or you can do it as a post-processing. So once the data is already collected, you can combine those sources and compute the inversion in a far faster fashion. So let me show you some of the examples. So here's the Marmousi velocity model. This is what you can reconstruct with all the data. So that's as good as it's going to get. People have been trying to use those sources to combine them in a random fashion, so using Radmacher or any other way to combine sources together. But if you are selecting an optimal selection of those, or not necessarily random weights, but optimal aggregation of your weights, you can actually recover something that looks like that is far more similar to what you can get in optimal settings as opposed to what you would get. And this is the state of the art, right? So people are already very excited to get this one. So the next part of the talk will be about a topic which is sort of orthogonal. So I spoke about experimental design, but the other question that we can ask ourselves is how can we incorporate consistently structure in the solutions we have. So we all know why regularization is necessary. It helps us to impose a priori information, stabilize the inversion process, and so forth. If we look at our problem, the real question is what to put here, right? And one approach is being explicit. So we can prescribe some functional, and there are many choices to do that. And the other approach is a little bit more implicit, and that links to sparse representation. So in this slide, you can see it's more of an evolution of the different things that people have attempted to put in as that prior. So starting with penalizing just for the energy, later on looking at local smoothness. So that's just an L2 with some discrete differential operator that essentially requires all nearby pixels to be similar, going with different covariances for having more adaptive smoothing through total variation that was mentioned here today, where we move from L2 to L1 norm. Then looking into robust statistics, Huber, and so forth, using wavelet sparsity. And really the buzzword nowadays is sparse representation, where we try to find the model that would be a composite of a dictionary by some sparse vector. And in order to impose that this vector is sparse, we would like to minimize this term, the L0 norm. And Tanner was talking about that actually yesterday. So just to give you a bit of understanding of what sparse representation is all about, essentially we believe that the true model can be described by a small number of parameters, or in a simple manner, right? And there are many ways to combine the model or to have generative models, one of which, and the simplest one, is actually to have just a product of a dictionary, which is an overcomplete set, by a sparse vector, and get the model. So let's say that I would like to represent a smiley face. So if I will follow the sparse representation approach, I would just pick up, it's like a feature space. So I will pick up a circle, two eyes, a smile, add them together, and get my smiley, as opposed to conventional representation in which I would have to say black, 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 white, 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 black, black, black. By the time I will finish just describing this, probably all of us will be out for beers, right? So using a sparse representation is a far efficient way to describe things, and I'll talk about it a little bit more in depth in a few slides. So ideally, we would like to use the so-called L0 norm penalty. It's non-convex, NP-hard combinatorial problem. So instead, we use the tightest convex relaxation, which is the L1 norm. So all we do is we take the inverse problem we have, and we replace the model by a product of the dictionary by the sparse vector, and we put as a regularization penalty that vector is indeed sparse. So we penalize the L1 norm of that vector, right? So how well does it work? On the top left, you can see a model. We took some point spread function, so we blur it. That's the data on the top right. And here are several recoveries of that model with different options, including total variation that, again, is considered as one of the most promising approaches used in the industry, right? So I don't know whether we need to vote here, but then whether you can see that from afar, but here you can actually see more structure. Some internal structure that you wouldn't see in a total variation or any other approach. I hope that I even can convince you, right? It's an overcomplete DCT, overcomplete discrete cosine transform. But that's actually a very good question. You're ahead of the gang. So here is another example. We have a picture of Barbara from MATLAB. We can take out 30% of the pixels or 60% of the pixels. And as we try to recover that, we can get fairly nice recoveries, but that's really not the point. The point is that using a different observation operator, you can see that this recovery is slightly different than this one. So the operator that I used for recovery actually matters for my reconstruction. And that's an important point. Here's another example. We have this parrot. and I don't know, now I have a small daughter, so I take her to the zoo often, and you take a photo of a parrot or whatever, and it is always behind the bars. So you would like to free this parrot, free Willy, right? And so let's say that my observation is only at the black parts of this matrix, or this lattice. And trying to do that with two different dictionaries, back to Adrian's question, would give us two different results. So if you look at the beak of the parrot here, as opposed to the beak of the parrot here, obviously it is different. I cannot say which one of them is correct, but it is different. So the choice of dictionary makes a lot of difference in what we can recover. And lastly, if you think that sparse representation always works, I can show you some examples where it doesn't work, and that's actually important itself. So let's say that you have this image of a satellite, and that's the data that you really collected using one approach, which is the hybrid approach that Eldad was mentioning earlier. Provide this recovery using an overcomplete wavelet dictionary. You get this recovery, which I would hopefully have an agreement that it's not as good, right? So if we ask ourselves what's really is going on here, we can see that the performance of sparse representation is case dependent, and it depends on the model space that you consider. And in most situations, you cannot really control that. So you cannot, on a medical setting, say, you know, I really don't like this guy. I would like to take the other guy to the scanner. You cannot do that, right? Another thing that you cannot control is the operator. So if the physician prescribed you to send somebody to an MR scan, you cannot say, why should we take an MR scan? I just got this new cell phone with a brilliant camera. I will take a photo of the camera. We cannot replace that, right? So you have to stick to the operator that you've been assigned to. But what you can control is the dictionary. And some dictionaries perform better than other dictionaries. So one approach is to say, this dictionary is an overcomplete set. So I can just take recommendations of my peers as for what worked for them, and just make this huge dictionary. And different transformations that people have tried in order to do that. We were very critical about this approach. We said that, you know, that's really the difference between objective and subjective function that you try to minimize, because your own heuristic choice of what should you put in that dictionary affect what you will recover, and that makes the whole interpretation very, very biased. You would like the solutions to be as bias-free as you can, and the question is how to do that. You can try to design or learn the dictionary from some authentic examples of the model space. So we know that nature is not random. We should not try to treat it as random when we do the reconstruction. This is what we typically do. The problem with that structure is that, and then I think it was mentioned here, the clinician or practitioner can easily identify when you see a subsurface, or when you see a brain image, despite noise or whatever. He can readily do that. And he can really identify a tumor or something of that sort. But if you will ask him to, can you please write me the functional that you were using in your eye to do that, most of them, or actually none of them, would be able to do that. So it's very difficult to prescribe mathematically what our interpretation process is doing. But if we can incorporate that already in the inversion, rather than do it as a post-processing, that has a lot of value. So designing the dictionary allows you to be adaptive. So you are adaptive to the model space, the operator space, and the statistics of the noise. Because it is an overcomplete set, there's nothing that you cannot represent with that. So all solutions are viable. And since you are using the right terminology, you are very, very precise and prescriptive in what you say. You can communicate the message in a very clear and robust manner. So looking into the statistical merit here, we might feel like a deja vu, because the very similar arguments would hold here. So I'll just skip that one, and we can go to the conclusion that you can use an empirical estimate of the Bayesian risk. This time you would try to find the models, or you try to find the dictionaries that the models that you will recover with will be as close to the true models. And you, again, need to bear in mind that that's the design problem. Underneath that, we have an inverse problem that we need to solve. So again, we have these bi-level optimization problems that are not very friendly. Here, this one is actually even less friendly than the other one, because in the lower level, here we put something which is not continuously differentiable. So that can be quite tricky. What we do is we replace this non-smooth L1 norm with a smooth optimization problem with the inequality constraints that this U sparse vector is decomposing to the difference between P and Q. Both of them are positive parameters, as you typically do in linear programming. And then you can differentiate the sensitivity relations, and that's a bit of a long and tedious exercise. But the important thing is that so the sensitivities really depend on the observation operator that you have, and that's important. So by variation of the Bayesian risk, you can actually have this term, which the Jacobian multiplied by a change in the dictionary. You can derive the gradient, and once you have the gradient that depends on those sensitivities that I mentioned, you can update your model. You have to be a little bit careful here, because this statement is only valid in the neighborhood of the activities of Q and P, right? So because as we change D, and Bonas, I think, and others have written nice papers about that, we actually change the active set. We need to consider a non-smooth optimization framework, and we use the modified LBFGS of overtone in order to overcome that difficulty in the reconstruction. So let me show you some numerical results. So here is the true model. That's the data that we collected with some noise. Here is what you can recover using a prototype dictionary. So let's say I think this one was an overcomplete discrete cosine transform, which is not bad, but as you can see, you can do far better if you learn the dictionary. And if you compare it to total variation, I think you can definitely see that it is far superior. You can see some of the internal structures here that are not evident at all in total variation. Now, how robust this is with respect to noise, and I mentioned that you also learn the noise characteristics of the problem, that's another benefit you may have. So if you look here, we have 0.1% added noise, 1% and 5%. Looking at using a conventional prototype dictionary, as we add more and more noise, the quality degrades significantly. When we learn the dictionary, we are quite robust, although this image is not as good as this one, but you can still see the corpus callosum and some of the other structures in the head, which is wonderful. And total variation, as expected, become completely speckled, because it tried to define those piecewise constant regions that makes this image just a bunch of uniform stains. And you can do actually the same thing for other problems where the model space and the data resides in other spaces. So I'll skip that then next variant for the interest of time. So let me summarize a few interesting quotes on that regard, I hope, and that will be the end of it. So Einstein once wrote, what I can see in nature is a grand design that we can comprehend only imperfectly, and must fill a thinking person with a feeling of humility. And I think that's definitely right. Another good advice is don't try to design for everyone or for everything, because this is really impossible. You end up designing something that makes everybody unhappy. And when you think about it, there is no design that can win everything. You cannot have a car that is both the fastest car, but also the most safe and robust and if economical with respect to gasoline or whatever. You have to decide what you're trying to optimize it with respect to, and stick to that. And the last one is it's art if it can't be explained. It's fashion if no one asks for an explanation. It's design if it doesn't need an explanation. So that sort of renders my old talk as redundant, but hopefully I still managed to deliver something. So just to wrap up, I showed you generic approaches for designing ill-posed problems. One was related to learning the regularization. The other one was related to designing the experiments. From the long stack of list of different things that one can improve holistically in the inversion, these are only two components, but two that I believe people have not really addressed sufficiently thoroughly until now. So these are very interesting topics. And they introduce some interesting frontiers both in inverse problems and in optimization. One last thing is we do have some open source code. We have a collaboration with the University of British Columbia with Eldad. We have open source code for doing design for experiments. If you would like to try it yourself or send us some comments whether it works well for you or not. And with that, I would thank you for your attention. Thank you.
Quick questions. We're actually in tea time.
I don't think it's very fair to compare dictionary-based approach with total variation, because total variation actually is also sparse representation only for gradients. So when you use dictionary, you just use more data. You can use total variation regularization with dictionary, and probably results would be even better.
I would disagree on this one. So you don't use more data. That's a given, right? I have the same data at my disposal, and I can do whatever I want with that. Now, what I'm trying to argue is that if I'm trying to image something that looks like a brain, I should think about features, or building a dictionary that would have pieces of brain as the building blocks of that structure, and that will be probably more robust than taking something generic as total variation. But I'm not using any more data. I'm using more knowledge. So obviously, before I go into reconstruction, I know that I'm about, and I agree completely. So there will be a very different design of dictionary for capturing text versus capturing stars, constellations. And I think that's fair enough, right? We know that we're about to do that. Why shouldn't we optimize our inversion to be more appropriate for the sort of spaces that we are trying to recover the images for? So I'm being more prescriptive rather than using more data. It's the same data that I'm using.
So can I suggest that we take more questions over tea, and we just thank the speaker again. Thank you very much.